In this video, I'm going to solve a few problems on planetary motion. These will involve orbit, they will involve Newton's law of gravitation, and centripetal force. Okay, we have a planet with a mass of 5 times 10 to the 24. That's the mass of the planet. The planet is big. It has a large radius. A moon has a circular orbit around the planet. I'm going to give the drawing to you, but let me show you what it will look like. The moon is what circles. Right? We've been given the radius of the planet. There's the mass of the planet. We've been given the mass of the moon. And the moon goes around in a circle. Alright then, let's see. We also are given the mass of the moon. Yeah. And the radius of the planet, which is like this distance here. This tiny little distance. Radius of planet, radius of... that's the radius of the moon. The final thing we're given is the distance from surface to surface. From the surface of the planet to the surface of the moon, which I'll just call d, and it's 82 megameters. We have to find the moon's orbital speed. We are looking for v. The way we find v is by equating two different forces. The moon is moving around in a circle, so it feels a centripetal net force. What provides the centripetal net force? The answer to that question is gravity. So on the left side of the equation, I'm going to put Fg is equal to the centripetal net force. Fg can be replaced, according to Newton's law, with big G times the product of the masses over r squared. The masses we're dealing with are the mass of the planet and the mass of the moon. On the right side, I have mv squared over r. That's the equation for anything going in a circle. Now, the mass that I choose is not the planet's mass, because the planet is not the thing moving in a circle. The planet is not the thing whose speed I'm calculating. I'm looking for the moon's speed, therefore I need the moon's mass. Okay. So let me take this stuff away. And we'll keep the planet around. Okay. What happens here? We cancel out the mass of the moon. We cancel out one of these r's. And v is simply equal to the square root of g, which is, a value we know, 6.67 times 10 to the negative 11. G times the mass of the planet, 5 times 10 to the 24, over r, and r is the total distance. In this equation, r is the total distance from center to center. In other words, r is this plus this plus this. So let me find r up top first, and then I'll plug it in right here. Okay. This is a big long radical here. Hang on. Make that black here. Good. What is r? That's the question, so that I can plug it in right there. r is the sum of the three distances: the radius of the planet, which is 6 megameters, plus the radius of the moon, which was 0.4, plus the surface-to-surface distance, which was 82. I can add those up like this because they're all in megameters. They're all in the same unit. And when I add 86 and 2, I get 88. And then I have the 0.4. Megameters. I'm going to come back down here and plug in the value. 88.4. Mega is 10 to the 6. So in this equation, I must plug in meters for r, which is why I have the 10 to the 6 right there, because mega is 10 to the 6. Okay, you calculate this on the calculator, and what do we get? This computes to 1942. Oh gosh, my colors keep switching on me. 1942 meters per second. And let me round that for sig figs. I look at my givens back in the problem. Okay. This given, 5.0, has 2 sig figs. The power of 10 doesn't have any sig figs. So it's 5.0 has 2 sig figs. 6.00 has 3 sig figs. 4.0 has 2. And 0.40 has 2. And then this number has 4 sig figs. Of those givens, which has the least, or what's the least number of sig figs from the givens? It's 2. So my answer I here round to 2. Right here I round that answer to 2. Then we find the orbital period. Speed is distance over time. And let's see, I'll do the second line. If I plug in a time of the orbital period, that's the time it takes to go once around the circle. The distance that we travel as we go once around the circle is a circumference. So then we solve for t. T is equal to 2 pi r over d. Plug in the value of r from above, 88.4 E6. Whoa! Over v. That's weird. So I plug in 88.4 E6. We divide by v. But which value do I use? The answer is, in subsequent parts, you always use the unrounded value from before. Rounding is something we do only when we report our answer, not when we compute additional quantities or values. Okay, so what does this come to? 2,9,0,0,0 when we round for sig figs, like that. Alright, next one. And I'm going to do this one a little bit quicker. More quickly, I should say. We have a planet. The mass is given. Here's the moon. Its mass is given. The radius of the planet is given. The radius of the moon is given. The surface-to-surface distance is also given. Radius of planet, radius of moon. The distance from center to center is the sum of those 3 values. And that distance from center to center, r, is 9 megameters plus, what is it, 0.2 plus 95. So that's going to be 104.2 megameters. I'm going to find, what am I finding? The orbital speed, once again. I find the orbital speed by saying, hey, this thing which is moving in a circle feels a force of gravity and nothing else. Gravity provides the centripetal force. So then I plug in for the left side. That's planet over r squared. And I plug in for the right side. I think, what is it that goes in a circle? What is it that has a centripetal net force equation applying? The moon is what travels. That's what's going in the circle. Oops. The moon's mass cancels. R cancels. We're going to square root both sides to isolate v. And what do we get when we plug in our answer? It's going to be the square root of g times the mass of the planet, 8e24, over r squared. I'm sorry, just regular old r. The squared canceled out with that r. So it's going to be over 104.2. I can't plug in with megameters. I have to change it to meters. So I replace the mega with what it equals. Mega is 10 to the 6. So even though it's written with the mega here, I've replaced it with 10 to the 6 right there. Okay. And I compute. This comes 2262.9. So I round that with sig figs. How many sig figs does the answer get? This given has 2 sig figs. that has 3, that has 2, that given has 2, that one has 4. The least number of sig figs from the given, or the fewest number, smallest number, is 2. So 2 is the number of sig figs my answer has. Boom. Now we find the moon's orbital period. So by the way, right, did I say this? They were looking for orbital speed. The way we find speed is by equating gravity force with centripetal net force. Now we're going to find period. We're looking for t, capital T, which is the time it takes to go around once. Speed is distance over time. If I plug in the time interval of big T, that means we've gone around once. The distance we travel in one orbit is a circumference. If we solve for t, we get 2 pi r over v. Plug in values, right? R is this, and v that you use is the unrounded value of speed. And what do you get? This comes with rounding. I'm going to round it to 2 sig figs like above. And with rounding, it's 2,90000. And the answer here is given to us in seconds. Right. Next problem. This one's a little bit different. We now are given information about a star and a planet. It says that the planet has a circular orbit around the star. See that? So now, at the middle, is a star whose mass is given. And then over here is not a moon, it's a planet. So there might be moons going around the planet, but we don't care about that right now. At this point, we're going to look at the planet's circular motion around the star. And that's okay. We have the exact same method as before. We are given the radius of the star. Right? There's that value. We're given the mass of the planet times 10 to the 24. And we're given the radius of the planet, which is this little sliver of distance. And then we're also given the surface to surface distance, which I'll call d. Big R, little r rather, is the distance from center to center. And that value we get by adding up all of the 3. So it's going to be 540 megameters. I have to change it to times 10 to the 6. And the reason is because this distance is not in megameters. So it's 540 times 10 to the 6 plus 2 times 10 to the 6 plus 6 times 10 to the 11. And guess what? That's going to come out to almost 6 times 10 to the 11. Let's see. Yeah, it's, whoops, 6.00542 E11. We could probably just call it 6E11 and be fine. Now the planet is moving around in a circle, which means it feels a centripetal net force. What pulls it in? The answer is the gravity. That's what provides the centripetal net force. So on the left side, I plug in using Newton's gravitation equation. Planet and sun are what we're looking at now. What's moving in the circle? What do I plug in on the right? Which mass do I use in the circular motion centripetal net force equation? The thing moving in a circle is the planet. So you use its mass. The planet is what has circular orbit. So that's m planet. The mass of the planet cancels. One of the r's cancel. And speed is going to be square root of g times mass of the star. See that? We're using the star's mass, which is 7e30 from above. And all of that is over the total r, which is this value. Let's just call it 6.005 E11. So the answer here is 27,883, which rounds to, let's see, the fewest number of sig figs from the givens is 2. So that rounds to about 28,000 meters per second. That's how fast the planet goes. What's the orbit, the period of the planet? We use the same method from before.